An eroded rock wall rises against the black backdrop of space, horizontally illuminated by a sun that never sets. What secrets lie hidden in the perpetual darkness of the lunar South Pole? The descent into the depths of the Shackleton Crater reveals the exact spot where the Artemis III mission will touch down on the surface. The rim of this geological formation stretches for 21 kilometers of fractured rock and ancient dust. The basin's interior plunges into an abyss of 4 kilometers deep, a steep incline where direct sunlight hasn't touched the ground for over 2 billion years. Orbital probes have recorded an extreme thermal contrast in the topography of this boundary. Just a few meters from the upper ridge, constantly warmed by solar radiation, the crater floor maintains an absolute, unchanging darkness. A continuous environmental anomaly that has transformed this depression in the terrain into a natural vault, shielded against the temperature variations of the inner solar system. The natural vault mapped by the probes demands a drastic shift in the space navigation we've come to know. During the Apollo program, the 6 crewed moon landings occurred in the satellite's equatorial region. The terrain consisted of vast plains, illumination fell from above, and the line of sight to the communication antennas on Earth remained clear and direct. In April of 2026, the Orion capsule of the Artemis II mission descended into the Pacific Ocean, concluding a 10-day orbital journey. 4 astronauts tested the life support systems and the integrity of the heat shield, venturing over 400,000 kilometers from our planet. The free return trajectory around the Moon validated the flight computers without needing to activate the main thrusters for the return. The successful conclusion of this orbital architecture paved the way for the surface phase. Artemis III will leave the safe plains of the equator behind, pointing its descent radars toward the rugged and shadowy geology of the South Pole. The geology of the South Pole harbors dozens of deep craters that act as permanent cold traps. The Moon's rotational axis is tilted by just 1.5 degrees with respect to the plane of its orbit. Because of this almost perfectly straight angle, the Sun hovers eternally along the polar horizon, moving laterally without ever rising into the black sky. The highest peaks of the rims receive continuous light, creating islands of uninterrupted solar energy. Just below, on the isolated floor of basins like Shackleton, the temperature plummets to minus 230 degrees Celsius. The LRO probe's laser altimetry instrument scanned this darkness for years. Without relying on external light, the equipment fired millions of infrared light pulses directly against the crater floor. The photons reflected on the invisible ground and returned to the orbital sensors, carrying a thermal and reflective signature highly unusual for standard lunar geology. But the signature read by the sensors didn't just indicate volcanic rock and gray dust. Why does human survival in deep space depend on a frozen basin? Telemetry data revealed high albedo areas, highly reflective surfaces hidden beneath the first few centimeters of regolith. Neutron spectrometry confirmed the exact chemical composition of these highly reflective anomalies on the dark floor. They were massive deposits of water molecules delivered by comets and asteroids throughout the solar system's history. Without an atmosphere to retain heat and without direct solar radiation to sublimate the material, the ice remained trapped on the polar basin floor. It's not a smooth, solid ice layer, but microscopic crystals intimately mixed with abrasive lunar dust, an untouched reserve of primordial water, accumulated grain by grain and preserved in the vacuum over geological eras. The primordial water mixed with dust dictates the exact coordinates where the lander must descend. The architecture of Artemis III demands a navigation precision that 20th century missions never encountered. The Starship HLS vehicle, with its imposing 50-meter height, will not land on the dark floor of the Shackleton Crater. Down there, power generation from solar panels would be null, and radio contact with mission control on Earth would be physically blocked by the rock walls. The target is the illuminated rim, specifically a narrow ridge connecting the Shackleton Wall to the adjacent de Gerlach crater. Astronauts will descend into a challenging optical environment where the low sun casts black shadows kilometers long from rocks just a few centimeters tall. The proximity between this light-bathed ridge and the frozen abyss allows for the planning of spacewalks to the shadow zones. The water extracted from the floor won't just serve to fill the crew's life support tanks. Its molecules will be electrically separated into liquid hydrogen and liquid oxygen, the exact chemical formula of the propellant that fuels rocket engines. The propellant refined from polar ice changes the economics and scale of long-range exploration. The perpetual darkness of the Shackleton Crater hides the most valuable logistical resource in the near cosmos. It's not just an intact geological record of the solar system's past. It's the physical foundation of a sustainable interplanetary infrastructure. By establishing a landing zone on the illuminated rim to access the reserves of the dark abyss, Artemis III transforms the natural satellite into a fueling station for future missions toward Mars. In our next episode, we'll investigate the dusty basin of Mare Tranquillitatis, the exact spot where Apollo 11 landed in 1969 and no one returned. The Eagle lander rests in silence on the gray plain, casting a solitary shadow against the void.